Three seismic signals have pushed the western United States back into a difficult place this spring. A new look at the Cascadia Subduction Zone and the San Andreas Fault suggests the two systems may not always behave as separate problems, while southern Utah has been shaking through a swarm that reminds planners the interior West has its own fault burden to carry. How much strain can one fault system absorb before another responds? How close can two very different tectonic settings come to moving in sequence? And what happens to emergency planning when the risks are not isolated but layered across the coast and the basin and range interior? Cascadia and San Andreas are not the same kind of fault, and that difference matters. Cascadia is a subduction zone where the Juan de Fuca plate dives beneath North America along the Pacific Northwest margin. The San Andreas is a transform boundary where the Pacific and North American plates grind past one another through California. The two systems meet in the broad Mendocino Triple Junction region near Cape Mendocino, where the plate geometry becomes especially complicated. That junction is one reason the hazard conversation along the West Coast has never been simple, even before anyone began asking whether one fault might help set off the other. The study now driving that question did not begin with a plan to link the two faults. It began with a navigational error during a research cruise in 1999. The original target was the Cascadia margin, where scientists were drilling deep-sea sediment cores to read the record of past earthquakes. But a latitude entry error pushed the drill ship about 90 kilometers, or 55 miles, south of Cape Mendocino and into San Andreas territory. Instead of a failed detour, the mistake produced a core from the Noyo Canyon off Northern California that later became central to the argument. That core showed something unusual. Turbidites, the sediment layers left by fast-moving underwater landslides often triggered by earthquakes, usually have a standard grain pattern, coarser material below and finer material above. In the Noyo Canyon sample, researchers saw repeated paired layers, including cases where the layering looked inverted. The same paired behavior appeared in other cores north and south of Cape Mendocino. Once those layers were dated, the pattern became harder to dismiss as coincidence. More than half of the turbidites in the records from both sides of the junction lined up in time within the limits of radiocarbon dating. That timing is the key issue. The researchers concluded that one layer in a pair can be read as a response to Cascadia shaking and the other as a response to movement on the nearby San Andreas Fault. In some cases, the evidence suggests the second event followed the first within minutes or hours. The study therefore points to partial synchronization rather than perfect lockstep, but even that smaller claim changes the hazard picture. It means the coast may not always be dealing with one isolated rupture, and then, much later, another. It may sometimes be dealing with two major fault systems moving in a compressed sequence. The timing range matters because the record is not based on one layer or one century. The Oregon State University team analyzed deep-sea sediment cores representing roughly 3,100 years of geologic history. In that span, the strongest evidence for near-coupled ruptures appears in a handful of cases, including the event around 1700, which is especially important because it sits near the boundary between historical memory and geologic inference. The study also treats the older pattern cautiously, because sediment records can be complicated, but the repeated alignment was strong enough for the authors to argue that the doublet structure was best explained by two earthquakes in close succession, rather than by aftershocks or random sediment behavior. There is also a broader context behind the claim. Geologists have discussed fault synchronization for decades, but the real-world examples have been rare. The OSU release notes one observed case in Sumatra, where major earthquakes occurred 3 months apart in 2004 and 2005. Against that background, even partial synchronization along the North American West Coast is notable, because it adds a second dimension to the familiar Cascadia danger. A Cascadia rupture does not have to be the only major event in the emergency window for it to reshape the response problem. The study's importance also comes from how it reframes the worst case. A magnitude 9 or larger Cascadia earthquake is already capable of overwhelming transportation, communications, and response capacity across the Pacific Northwest. The new work suggests that the state of play could become more severe if the San Andreas were to follow closely behind. The Geological Society of America's release says the possibility of a near-simultaneous sequence raises questions about how much of the Pacific coast might be affected at once and how fast national resources could be stretched if multiple metropolitan regions were dealing with major shaking in the same compressed period. That is not the same as saying the faults are coupled in every event or that a Cascadia rupture guarantees a San Andreas rupture. The study itself is more measured than the headlines around it. It identifies a pattern in sediment layers, a plausible timing relationship, and a likely explanation tied to turbidity currents and earthquake-generated landslides. It does not turn the coast into a clockwork machine, but it does widen the frame. The western margin is not just a place where one great fault can fail. It is a place where several tectonic systems sit close enough together that one may leave evidence of the next. That is only part of the picture, though. While the coastal fault systems were back in the spotlight, southern Utah was showing its own active behavior. On the morning of April 19, 2026, residents in southern Millard County experienced a swarm of small earthquakes near Kanosh. By the next day, the Utah Geological Survey reported at least 32 recorded quakes in the sequence, with the largest measuring magnitude 3.6 at 8:43 in the morning. The cluster began around 5:45 in the morning and was centered roughly 13 kilometers, or 8 miles, south of Kanosh and about 29 kilometers, or 18 miles, south of Fillmore. The Utah swarm matters because it was not a single main shock followed by a neat trail of aftershocks. The state geological release described it as an earthquake swarm, meaning many small to moderate events occurring in a short window without one dominant rupture. That distinction is important in seismic reporting because swarms often look messy in the moment, but they are not unusual in a tectonically active region. In Utah, they are part of the state's normal geologic behavior, even when they still unsettle people who live through them. The location of the Kanosh swarm points directly to the Intermountain Seismic Belt, the zone of earthquake activity that runs through Utah along the eastern margin of the Basin and Range Province. The Utah Geological Survey says the crust there is thinning and stretching east to west, which causes it to break and shift along faults. That stretching is the basic engine behind many of the earthquakes in the region, including swarms that appear without much warning and then fade on their own. In other words, the seismicity is not random noise. It is the surface expression of a crust that is being pulled apart. The Kanosh sequence also sits next to another geologic feature that keeps the story from being too simple. The swarm occurred along the eastern side of the Black Rock Desert volcanic field, which the Utah Geological Survey describes as the youngest volcanic area in the state. The release is careful on this point. The swarm is not treated as evidence of an impending eruption. Instead, the agency says the old volcanic plumbing beneath the area may still be active enough for heated water or gases such as carbon dioxide to migrate through tiny cracks, lubricate shattered faults, and help trigger small earthquakes. That is a very different explanation from magma rising toward the surface, and it is one reason the swarm belongs in the earthquake file rather than the eruption file. Taken together, the Cascadia San Andreas study and the Kanosh swarm reveal something larger than any one fault zone. The western United States is being asked to carry multiple kinds of seismic risk at once. A subduction margin capable of producing a very large offshore rupture and tsunami, a long transform fault through California capable of severe urban shaking, and an interior belt of stretching crust that can produce swarms and damaging earthquakes of its own. Those systems work by different mechanisms, but they all land on the same practical problem. Emergency planning is easiest when hazards are separate, and much harder when they can overlap in time or geography. That overlap is what makes the West Coast findings more than an academic debate. The Oregon State University and GSA materials point to a seismic history where Cascadia and the northern San Andreas may have moved close together more often than previously recognized, including the possibility of rupture separation measured in minutes or hours. The Utah Geological Survey, meanwhile, shows that the interior west is not waiting quietly in the background. It is already producing swarms tied to stretching crust and possible fluid movement. The combined picture does not allow a neat one-fault-at-a-time emergency model. It suggests a region where multiple layers of risk can become active in the same general period, leaving response systems to deal with more than one moving target. There is also a reporting lesson in the way these events came into view. The Cascadia-San Andreas connection was not discovered through a search for a dramatic headline. It emerged from a wrong latitude entered during a cruise, an odd core sample, and years of checking whether an inverted sediment sequence could be explained by two earthquakes rather than one. The Utah swarm likewise did not require speculation to be real. The quake counts, times, sizes, and location were all documented as the sequence unfolded. In both cases, the data are doing the work. That is why the combined takeaway is so stark. The Western states do not need a fictional disaster scenario to look vulnerable. The geology already supplies enough complexity on its own. The practical result is a preparedness problem that reaches beyond state lines. If Cascadia were to rupture and the San Andreas were to follow closely behind, coastal response resources could be pulled into a far tighter window than planners usually assume. If Utah continues to produce swarms in the basin and range interior, that adds another reminder that seismic risk in the West is not confined to the shoreline. The question now is not whether one headline fault is more dangerous than another. It is whether the region is ready for the possibility that earthquakes can arrive as linked problems, not isolated ones, and that the most difficult days may be the ones when the coast and the interior are both active at the same time. By this point, the phrase worst-case scenario no longer points to a single rupture on a single fault. It points to a chain of stress, movement, and response that could spread from one tectonic setting to another, while smaller inland swarms remind everyone that the continent's interior is not stable simply because it sits away from the ocean. The new Cascadia-San Andreas work does not predict the next great earthquake, and the Utah swarm does not announce an eruption. It does something more useful. It shows that the western United States is being shaped by overlapping hazards, and that the easiest assumptions about timing and separation may not hold when the crust begins to move. The deeper implication is that western seismic risk is not organized into neat compartments. The Cascadia Subduction Zone runs from northern California to southern British Columbia, while the San Andreas Fault threads through California in a separate tectonic style, and the Intermountain West carries its own earthquake burden through stretching crust and active faults. The U.S. Geological Survey describes Cascadia as a classic subduction zone and notes that it contains the ingredients for very large earthquakes, even though its earthquake rate is unusually low compared with other major margins. At the same time, the USGS continues to treat the Intermountain West as a serious seismic region in its own right, with hazard models that extend far beyond the coast. That is why the Oregon State University findings matter beyond the immediate question of whether two faults can synchronize. The study now circulating through the scientific and public discussion draws on deep-sea sediment cores collected near the junction of Cascadia and the northern San Andreas system, where underwater slope failures can preserve a record of past shaking. The work reports that several deposits appear paired in time, with some intervals suggesting one major earthquake followed by another within minutes or hours. The research grew out of the 1999 Cape Mendocino coring error, when the ship ended up about 90 kilometers, or 55 miles, south of its planned position and sampled material that later became central to the study. The scientific value of that result is not in any single layer, but in the pattern across many layers. The paper published in Geosphere and the Oregon State University release both describe a record spanning roughly 3,000 years, with repeated timing matches between Cascadia turbidites and sediment packages associated with the northern San Andreas. That does not mean every great earthquake on one fault automatically triggers the other. It does mean the edge of the North American plate may be more interactive than older planning assumptions allowed. In a region where a major offshore rupture can already affect ports, highways, fuel systems, hospitals, and communications across hundreds of miles, the possibility of a second major quake shortly afterward is not a side note. It is a planning variable. The same logic applies in a different way to Utah. The Kanosh swarm reported by the Utah Geological Survey involved at least 32 earthquakes by April 20th, with the largest reaching magnitude 3.6 and the sequence beginning around 5:45 in the morning on April 19th. The swarm occurred roughly 13 kilometers, or 8 miles, south of Kanash and 29 kilometers, or 18 miles, south of Fillmore, directly east of the Black Rock Desert volcanic field. The agency's release ties the activity to normal crustal extension in the intermountain seismic belt, while also noting that fluids moving through the shattered crust may have helped trigger the sequence. That fluid component is important because it shows how earthquakes can be generated without magma moving upward in any dramatic way. The UGS description points to an ancient volcanic field whose plumbing may still influence modern fault behavior through heat, groundwater, and carbon dioxide migration. In practical terms, this means a swarm can be geologically meaningful, even when it never develops into a larger event. It can reveal which parts of the crust are fractured, where pressure is changing, and how underground pathways are connected. The absence of an eruption signal does not make the swarm trivial. It makes it a useful window into the structure of the crust itself. Put next to the Cascadia San Andreas work, the Utah swarm sharpens the same broad message from two very different directions. On the coast, the concern is that large faults may not always behave independently. In the interior west, the concern is that active crustal stretching can produce clusters of earthquakes in places that many people still imagine as comparatively stable. The USGS has long treated the Intermountain West as part of the national earthquake hazard picture, and the Utah event is consistent with that view. It is a reminder that the western United States contains more than one kind of hazard engine. Subduction, transform motion, and extension all operate at once, even if they do so on different timescales and in different ways. That combination is what makes the phrase worst-case scenario feel less like a slogan and more like a logistical question. A Cascadia rupture already carries the potential for widespread shaking and tsunami impacts along the Pacific margin. A closely timed San Andreas rupture would compound the strain by adding another major transportation and population corridor to the response burden. Utah's swarms, while far smaller in magnitude, show that the inland west can also experience active shaking while the coast is under stress. Emergency systems are built to respond to major earthquakes, but the combined possibility of near back-to-back events in separate regions forces planners to think about how mutual aid, fuel delivery, communications, and hospital capacity would function if several parts of the West were demanding help at once. The geological record says this kind of overlap should not be dismissed too quickly. Cascadia's sediment archives preserve evidence of repeated large ruptures, and the new core analysis suggests that some of those events may line up with movement on the northern San Andreas. Utah's earthquake swarm shows that even moderate activity can arrive in dense bursts, rather than in a simple main shock-aftershock pattern. Neither setting fits a tidy one-event-at-a-time model. Both instead point to systems that release stress in ways that are episodic, irregular, and sometimes linked across distance. That is a difficult pattern for public communication, but it is also the pattern the data are increasingly describing. So the western United States is not facing one single seismic problem, but several that can interact in space and time. The coast has a plate boundary capable of producing enormous earthquakes and tsunamis. California has a long transform fault that can transmit stress through a heavily populated corridor. Utah has an interior crust that still breaks, swarms, and reorganizes under extension. The latest findings do not collapse those hazards into one cause. They do something more useful. They show that the boundaries between them are thinner than the public usually assumes, and that the region's real risk is not just the size of any one earthquake, but the way several different earthquake systems can press on the same calendar at once.